Record. Okay, so I hope you have all seen what a graph is before. I think I've been talking about them a little bit. Well, I've certainly talked about them when we did persistence. But you know, it's a set of vertices and a set of edges between pairs of vertices. And right, so usually you draw these things like this. The edges are points or circles usually, because points are invisible to the naked eye. And sorry, the vertices are circles and the edges are straight line segments or sometimes curves joining them. And a graph is planar if I can draw it the way that I've done here, so that yeah, the edges are, but the vertices are points, the edges are curves. They don't have to be necessarily straight line. And I can draw them in the plane like this so that no two edges cross each other except if they happen to meet at the same endpoint. Okay. So this is a plane drawing of a planar graph. So this drawing is a proof that this particular graph is planar. This drawing is not a proof that this graph is not planar, because this graph that I've drawn here is planar. I just haven't drawn it in a plane way. I could draw it differently by drawing this edge out here, and then I don't have any crossings. Okay. So planarity is a property of the graph itself, not of the drawing. It's just that the drawings are a handy proof that things are planar. Okay, so let's leave that there for now. So you've probably seen graph representations before. So what are the two representations that you typically learn about for graphs? Yeah. So there's two representations. One of them is called the adjacency matrix. And it is, so n will always be the number of vertices in our graph. M will always be the number of edges. And F will be the number of faces in some drawing of our graph. Okay. And what are the faces? The faces are the parts of the plane that you get if you you cut out all of the vertices and edges. If I did that here with a good sharp knife, the blackboard would fall apart into pieces. There'd be a big piece that's still stuck to the wall, and then there would be these bounded pieces that would fall on the ground. Each of those is a face. Okay, okay, so an adjacency matrix, basically it's a matrix with the vertices listed on it's indexed by the vertices on both the rows and the columns. And, you know, you put a 1 in the matrix at position ij if there is an edge from vi to vj, and you put a 0 in the matrix otherwise. So if I put a v k here, then there is no edge from vk to vj, so there's a 0 there. Yeah, so you get the idea. It's a great representation. Why is it a great representation? Well, it's great if your graph has a lot of edges, but it's not, and it's great because you can treat this matrix like a real matrix of numbers now and use algebra tricks to do things with your graph. But for planar graphs, it's not great, because planar graphs tend not to have a lot of edges, and this matrix has n squared entries in it, or you can cut it in half and realize that you only need half those entries, but that's still n choose 2 entries. So still quadratic. What's good about it, though, is if you give me Vi and Vj, or the indices I and j, then I can tell you in constant time whether or not there's an edge joining those two vertices. The other representation is the adjacency list representation, which is one array indexed by the vertices, and each vertex stores a list of the edges of the vertices to which it is adjacent. So for example, if I were to look over here in Vj's list, that's this one, I would find 1, 2, 3, 4 items. Most of them are unnamed in this picture, but Vi would be in that list. And if I were to look in Vi's list, I would find 3 items, and one of them would be Vj. And sometimes this is augmented for planar graphs to be able to do nice tricks, like walk around a face, for example, seeing all the edges or vertices of a face. And that's done with, well, sometimes you cross-link things. So in the occurrence of Vi in Vj's list, you put a link to the occurrence of Vj in Vi's list, and then you sort the lists, let's say counterclockwise in the drawing. But that's not the point today. The point today, and what's the other nice thing about this is that the space is just proportional to the number of edges. If you add up the lengths of all these lists, you get twice the number of edges, because for every edge, you get something appearing in this list, and you get something appearing in this list. What's not great about it is if I give you 2 vertices, Vi and Vj, and ask you if they're adjacent, that doesn't necessarily take constant time. And right, that's not even for complicated graphs. Just take some graph like this, for example. Call this one V1, this one V2, and this one V3. Well, to know if V1 and V2 are adjacent, I can look in V1's list until I find V2, or look in V2's list until I find V1, but it's not obvious. Well, I mean, it's not obvious that I'll find V1 or V1 in V2's list very quickly, or V2 and V1's list very quickly. And if I ask if V1 is adjacent to V3, then I won't know until I've basically examined their lists. So that's not good. And in fact, there's no reason that these can't be, I mean, even this graph, which has 2 vertices of degree n minus 1, no, sorry, not n minus 1, n over 2, that's a problem already. So that could mean that just asking if 2 vertices are adjacent takes linear time. Not good. So, good for space, bad for adjacency testing, bad for space, good for adjacency testing. And so this is sort of an easy warm-up problem for today. Is there some representation that's good for space and good for adjacency testing?
Can you make something like a dynamic metric?
You can make a fancy structure for storing this thing in a more compact way. But usually then you end up with the problem of checking if something is a 0 or a 1 means some kind of non-trivial search. Like, you could think of doing something like this with Van de Boas trees, and then it would take, let's say, log n time to know if two things are adjacent. It's way better than a linear time, than n time, but not great. What's that? Yeah, you can probably come up with some log n solutions with some divide and conquer, but that is not entirely trivial. Is there a way we could speed this up using just things we know from class? Yeah. So if this adjacency, if this list here, if I replace it by a hash table, then I can certainly do adjacency testing in constant time, right? If I want to know if Vi and Vj are adjacent, I go to Vj's adjacency hash table and see if Vi is in that hash table. That takes constant time. Now, okay, that's good. And if you can even use perfect hashing, so that will take worst case constant time, and the time to build it is expected amortized. But that seems like a lot of effort for something as simple as just being able to test if two vertices are adjacent. Surely there's a simpler way to do this. All right. So, does anybody know about Euler's formula for planar graphs? Yeah, so Euler's formula says if you add the number of vertices plus the number of faces, and you subtract 2, then you get the number of edges. Subtract 2, 2. 3, yeah, you get the number of edges. Okay. That's good. There is, I'll illustrate, it's not really a proper proof, but something that's going to help guide us a little bit later is, where does this formula come from? Okay. Where does this formula come from? Well, one way to remember it is the following. Take your graph and pretend for now, like this one, it's connected. And take a spanning tree of your graph. So that's a subgraph that is connected but has no cycles. Okay. There's a spanning tree. So that spanning tree contains all the vertices. So how many edges does it have? So the pink M. Well, every tree has exactly one less edge than the number of vertices that it has. And the number of vertices is n. Now, look at your faces. And connect two faces if there is an edge between them, separating them, that's not pink. So it's an edge that's not used by the spanning tree. And what you'll find is that you also get a connected graph, and this graph has no cycles. So there's a few ways to convince yourself of that, but why is it connected? Well, if it was not connected, that would mean you have some vertices of this thing, faces of this thing, and some other faces of this thing with no edges between them. So you could partition into two things like that. But if there's no edges between them, that means somehow there were edges between these faces in the graph somewhere, but they all got used up by this spanning tree. And how would this pink spanning tree, and how would that happen? Well, that means this pink spanning tree is supposed to separate these two things, but the pink spanning tree doesn't contain any cycles, so it can't separate one from the other. So that's why it's connected. And why does it have no cycles? Well, it's the same thing in the other direction. If my graph on the faces here had a cycle, well, inside that cycle, there must be at least one vertex, right? This is a bunch of faces that form a cycle. Somewhere in there, there's a vertex of my graph. In particular, there are edges of my graph, that go like this. So somewhere there's a vertex inside, and somewhere there's a vertex outside. But well, that means that I don't have there's no path from this vertex to that vertex, because well, yeah. Okay. So, and that means this pink thing, or this yellow thing, M2, is, well, it's also a tree. The number of vertices in that tree is F. There's one for each face, and then you get a -1. And now add these two things together, you get M plus F minus 2. Add these two things together, you get the total number of edges, M, all of them, and you get Euler's formula here. Okay. And this idea of a tree and a spanning tree, and the tree that remains actually is a really useful one in some of the things we're going to do today, and it's a really useful one in general. It's called the tree co-tree argument. Okay. One of the things that you can deduce from Euler's formula is that the number of edges is less than or equal to 3 times the number of vertices minus 6. Okay. Do you believe this? Do you want to know why this is true? Probably many of you have seen it before. Okay, so I'll leave that to you. Basically, you use the fact that every face has to have at least 3 edges on its boundary, and every edge is on the boundary of 2 faces. That will tell you something about F that you can use to get this. Okay, good. What else can I tell you about graphs? So this is about planar graphs. So the degree of a vertex, I didn't say it, is just the number of edges incident to that vertex, the length of its adjacency list in an adjacency list representation. So if I add up over all the vertices in my graph, the degree of that vertex, what does that add up to? 2 times the number of edges. So 2 times M. Why? Well, because you can think of it as counting the endpoints of the edges, and each edge has 2 endpoints, right? This edge will contribute once to the degree of this endpoint, and it'll contribute again to the degree of this endpoint. So it'll contribute exactly 2 to this sum, and that's true for every edge, so the sum has to be twice the number of edges. Okay? All right. Now, that tells you something. So you remember the pigeonhole principle says that if I take 2m pigeons and force them into n holes, then I will find some hole that has at most the average number of pigeons per hole. Okay. So what does that mean here? That means I'll be able to find some vertex v with the degree of v is less than or equal to 2m divided by n. M is less than or equal to 3n minus 6, so this is 2, in fact, it's the floor of that. So what is that? That is 6n minus 12 divided by n, which is equal to 6 minus 12 divided by n. This number here is less than 6, and we're taking the floor of it, so that's less than or equal to 5. Okay. So there exists a vertex v whose degree is less than or equal to 5. Classic result about planar graphs. What does it have to do with data structures that we're talking about today? Well, using this fact, I can order the vertices of my graph. So like this, I'll say my graph has a vertex whose degree is less than or equal to 5. So I'll call that vertex 1. And then I will, so I'm gonna list the vertices in some order. So what I know is that vertex 1 will have at most, after I'm done listing the vertices, I'll have to connect it to at most 5 vertices in the list. And now when I take vertex 1 away, the graph that I have is still planar. Right, taking a vertex away and removing all its incident edges, that doesn't introduce any crossings in the drawing of the graph. So that new graph that I have also has a vertex of degree at most 5. That's V2. V2 may be connected to V1, and it may be connected to at most 5 other things that I haven't removed yet. Just keep doing this, and you get a list of your vertices. So that if you look at any vertex, you see at most 5 edges going off to the right. You may see a lot of edges going off to the left, but at most 5 going off to the right. Okay, so let's think about this. So when I remove V1, take those 5 edges that are there and imagine directing them so that they're pointing away from V1. And now when I remove V2, I do the same thing. V3, V4, and so on. At the end of this process, every edge has been assigned a direction. But if I look at any vertex, the number of edges coming out of it is at most 5. Okay, good. So that suggests a data structure already that will work in constant time. So it's like the adjacency list data structure, but each vertex doesn't remember all of its neighbors. It just remembers its 5 special neighbors, the ones where the edges go out, at most 5. So now if I look at Vi and Vj, if there's an edge between them, that edge has a direction. if the edge is directed this way, then in the list of VI's 5 outgoing neighbors, I will see VJ. And if it's directed the other way, then in the list of VJ's 5 outgoing neighbors, I will see VI. So each vertex has a list of length at most 5. And to test adjacency between two things, I look for VI and VJ's list, and I look for VJ and VI's list. If I don't find either of those things, then the edge is not present. If I do, it is there. Okay. All right. Nice and easy. Now, that seems easy and trivial, but it's actually far from the end of the story for a very closely related problem. There's a long history of work on what's called adjacency labeling of graphs. So another way to think of this, what I just described, is I give each of my vertices a number from 1 to n. And so that sort of starts out as the initial label of this vertex. And then the rest of it, it has up to 5 more parts of its label, which are the numbers of the vertices of the edges coming that the edges coming out of it are pointed to. What's the point of that? Well, if I call that the name of the vertex, so maybe this is, x1, x2, x3, x4. So let's call this is the label of this vertex. Then if you give me the labels of 2 vertices, any 2 vertices, I can tell you whether they're adjacent just by looking at their labels. I don't need, it's not a particularly fancy data structure. In fact, it's not really a data structure. It's more of a distributed thing. I just name them so that by looking at their names, I can tell you whether or not they're adjacent in the graph. So the whole graph is encoded just in these labels. Now, these labels have size n to the 6, right? 1 identifier for the vertex and then 5 for its neighbors. So the number of possible labels is n to the 6, or if you measure that in bits, that's 6 log n. And for a long time, the question was, okay, so you can do 6 log n, and that follows fairly quickly from Euler's formula. Can you make this 6 smaller? Can you make it 3, 2, whatever? So this went from 4 down to 3, down to 2. So this took about 30 years, down to 4/3. And then finally, in the last year or so, it's down to 1 plus something that gets smaller and smaller as n gets bigger. Okay. So a lot of work on this seemingly simple problem that starts with this simple solution. Okay. All right, that was the warm-up. Let's ask a more complicated question about our graph. So there's a linear space data structure that tells me whether or not 2 vertices are adjacent. Now, for any 2 vertices in my graph, provided that it's connected, there are 1 or more paths between the 2 vertices. Maybe lots of paths, but there is some minimum length over all the possible paths between these 2 vertices. So that's called the distance between S and T in the graph, the length of the shortest path between them. So what if I would like, so the adjacency testing problem is the problem of asking if the length of the shortest path between these two vertices is 1 or greater than 1. But what if I want to know what is the length of the shortest path between these two vertices? So I give you the graph, you pre-process it to build a data structure so that if you give me any two vertices, I can tell you the length of the shortest path between them. Now, without any data structure, you may know about Dijkstra's algorithm that says you can answer that query in n log n time. So Dijkstra's algorithm on planar graphs solves the shortest path problem in n log n time. But in terms of data structuring, that's not terribly exciting, right? That means, yeah, if you can look at all the data and do some more work, you can answer the question. But you would like to do it without maybe looking at all the data. Turns out that this is a hard problem. Been studied for decades, still not fully solved, but we'll see sort of the early attempts at solutions. And in fact, one of the most important results about planar graphs. So in order to speed things along today, I'm going to be sloppy from this point onward when it comes to floors and ceilings. So there'll be some things that I say which are not quite true unless I take a floor, or not quite true unless I take a ceiling, but we'll ignore that for now. Here's a nice one, which is not quite true, but so every binary tree on n vertices contains an edge whose removal leaves no component with more than 2n over 3 vertices. And right away, if you're sharp, you'll say that's a lie, because there's an example right here. So binary tree is, for our purposes, is a tree where every vertex has maximum degree 3. You'll realize that's a lie, because any edge that I remove here is going to leave me with one component of size 1 and another one of size 3. This is of size 3n over 4, not 2n over, which is bigger than 2n over 3. So you actually have to take a floor here. Okay. Does anybody know how to prove this? So what's that? So any idea how to prove, for example, that this binary tree has such a nice edge? Is this edge a good one? No. If there is a good one, it should be over on this side, right? Like it should be over here. What about this edge? No. What about this edge? I don't think so. Yeah, so let's take every edge, and if it's not a good one, that means one of the two sides has more than 2n over 3 vertices on that side. So let's point that edge towards that heavy side. Okay. And I claim that if we do that, there has to be an edge that we don't point anywhere, meaning it has no side with more than 2n over 3 vertices on Why is that? Well, if every edge has a direction, well, we saw that at the leaves that the edges point towards the middle. So if every edge is assigned a direction, that means we'll eventually get to some vertex that has 3 edges coming into it. What do those 3 edges mean? Well, this edge here means that this side is, ceiling of 2n/3. This side here has more than 2n/3 vertices, more than the ceiling of 2n/3 vertices. This edge means that this side here has more than the ceiling of 2n/3 vertices. And this one says that this side here has more than 2n/3 vertices. And if you add all of that up carefully with the floor, you'll realize that would imply that the graph has more than n vertices, which that's not true. That's not possible. Okay, so you'll find an edge that has this this property. All right. So binary tree has a, I'm going to call it a 1/3, 2/3 edge separator. We'll remember that for later. Okay. Good. Easy. This, by the way, is already an incredibly useful property in data structures. So you can get all kinds of logarithmic running time data structures over trees or trees that are representing something just using this property. Okay. Now, well, let's warm before we jump into whole planar graphs. Let's try something really simple. Oh no, let's leave that for now. Let's go straight to the planar graphs. Okay, so that's what's called a separator theorem, and this is a really nice one. Just one edge, you take it away, you get something that's broken into small parts. For planar graphs, we get the following famous theorem. Every n vertex planar graph contains, let's call it G, contains a set of some constant times square root n vertices, call that set S, such that G minus S has no component of size greater than 2n/3. Okay. Super famous theorem, and we'll see that once we have it, this distance labeling problem, we can find a non-trivial data structure that, or this distance oracle problem, we can find a non-trivial data structure with maybe better running time than you would expect. Okay, how does anyone go about proving something like this? Well, let's try something naive. Take a vertex, any vertex you want in your planar graph, and you're going to build what's called the breadth-first search tree from that vertex. Okay, so that's a tree where the root is the vertex that you selected, and then its children are the neighbors of this vertex, and then these ones have all the children, so if you take the collection of all the children of these, it's all of the neighbors of all of these vertices, except possibly this one, because it's already in the tree. Okay. So what the breadth-first search tree does is you pick your favorite vertex R to be the root, and then the children of the root, these are all at distance 1 from R. The children of the children are all at distance 2. And so on. Okay. Now, what's important about the breadth-first search tree is, I mean, your graph has other edges in it that are not in the tree. For example, you could have an edge between these two distance 1 things. And you could also have edges, diagonal edges like this, for example. Great. But what you cannot have is an edge from a vertex to a vertex which is 2 or more levels below it. Why not? Well, these layers are sorting basically the vertices by the distance from the root. If this is distance 1, then this is distance 2, so it shouldn't be down here on level 3, it should be up on level 2. So all the edges go either, they stay within a single layer of this tree, or they go from one layer to the next, whether they're true. So tree edges always go from one layer to the next. The other edges may stay within a layer or go from one level to the next. So let's draw this thing abstractly and count the number of vertices at each layer. So we have some number of vertices in the 0th layer. That's just 1. It's the root. But then here we have some number n1 of vertices, which happens to be the degree of the root, and then we get some n2, n3, and so on, all the way up to nh for some number h. Okay. And if I add up all those numbers, I just get n, the number of vertices in the graph. All right. So we're looking for something we can take away that is going to split our graph into parts that are no bigger than size n/2. So it seems like a really natural thing to do here is start adding up these numbers as we walk down the tree. At some point, we'll have less than n/2. And on the next layer, when we add the next number in, we'll have greater than or equal to n/2. Okay. So there's always going to be some layer, ni, where if I add up n1 up to ni minus 1, that is less than n/2. And if I add up ni plus 1 up to nh, that's also less than n over 2. And so, yeah, taking away these things would leave me with two things that are of size at most n over 2. And if I take this layer away, then there are no more edges from up here to down here. There are no more paths from up here to down here because there's no edges of length 2. And when I take away these vertices, all the edges going up disappear and all the edges going down disappear, and there are no edges crossing this boundary. So this set here, this level I set, definitely has this nice, it could be our set S that gives us no component of size greater than, in fact, no component of size greater than n over 2, never mind 2n over 3. What's the problem with that? Ni could be huge, right? We don't know. This Ni could work out that actually Ni is n over 2. That's no good. Okay, but that still seems hopeful. I mean, it seems like a good start. So now remember, we're not aiming for exactly n over 2. We're satisfied with 2n over 3. So maybe if Ni is really big, we could think of just going out a little bit. Like maybe there's another, if we just went, one level off, maybe that would be okay. And maybe that wouldn't be too bad. In fact, from Ni, we can start walking up until we find something. Let's call this Na, which is has size less than or equal to square root of n. And we might as well walk down as well until we find some Nb, which has size less than or equal to square root of n. And these are the first, when I walk up, that's the first one with this property. When I walk down, that's the first one with this property. So everything before that, Ni minus 1, Ni minus 2, and so on, they all have size bigger than square root n. So in fact, every level between Na and Nb has size bigger than square root n. So how far apart can those two levels be? Yep. So B, you certainly must have B minus A minus 1 is a less than or equal to square root of n. B minus A minus 1 is the number of layers in between. Each layer has root n vertices in it. If there were more than root n layers in between, each with more than root n vertices, then we have more than n vertices, which doesn't make sense. We only have n vertices total. Okay, so we can find a couple of layers that are small enough, and they're not too far away from the layer we were shooting for. So what's the picture look like now? Here's our tree. We have an A and B. We started out that everything above Ni, there was less than n over 2 vertices there. So certainly everything above Na, there's still less than n over 2. It's even less than there used to be. And certainly below Nb, there's less than n over 2. All right. But if we take them away, there's still this big chunk in the middle. And I can't tell you if that's big or small. Right? Like I said, the level Ni itself could have had nearly all the vertices. So for example, there's a planar graph with n minus 2 vertices here, one on top, one below. This is the Ni. Indeed, we can back off and find something that the Na and Nb, but the stuff between Na and Nb is huge. But at least we know that there's nothing much above Na and there's nothing much below Nb. And in particular, this kind of now lets us not worry about the fact that the tree might be really tall, because even if the tree is really tall, there's only sort of a stretch of size root n in the middle that we care about, that we have to worry about. But how are we going to deal with this? Okay. Here comes the cool stuff. So, one nice thing about planar graphs is that I really understand what the planar graphs look like with the largest number of possible edges. In fact, I know if I know what the number of vertices in my planar graph is, and the graph has as many edges as possible, then I know that the number of edges is exactly 3n minus 6. That matches that bound that we talked about. And I know that every face is a triangle, and I even know the number of faces will be 2n minus 4. You can get both of those things from Euler's formula. That's when you have as many edges as possible. And if you have a planar graph that doesn't have as many edges as possible, I don't know, what does that mean? Maybe it's a graph that looks like this. Does it have the maximum number of possible edges? No, because I can see faces that are not triangles, and on any face that's not a triangle, I can add an edge between. There are two vertices of that face that are not. Well, there's an edge that I can add between two vertices of that face to get one more edge in my graph. So I can triangulate my graph until I get something that has as many edges as possible. Okay. So in this graph, every face is a triangle, including the outer face, which is the complement of a triangle. So this has as many edges as it can. And for what I'm trying to do here, which is to separate the graph, to find some vertices that I can remove that won't leave any components, adding edges like this is just going to make it harder for me. Because, because that just creates more possibilities for, after removing the vertices, for the graph to stay connected. So I can assume that the graph that I'm trying to prove this on is a triangulation. Okay. All right. So I have a breadth-first search tree of my graph. I don't know. This is going to be a boring one probably, but for this graph, if I pick this as the root, here's my breadth-first search, the beginning of my breadth-first search tree. There's level 0. Here's a level 1. And then comes level 2. And then that's it. There's nothing left. Okay. Good. Let's think a little bit about this. So my graph has no cycle. The spanning tree has no cycles because it's a spanning tree. The breadth-first search tree has no cycles. But it has n minus 1 edges, like all trees on n vertices do. So if I add an edge of my graph to this tree, I'm going to create a cycle. In fact, I'm going to create exactly one cycle. So for example, if I add this edge, then that closes a cycle. like this. Okay. All right. What can you tell me about that cycle in terms of well, in terms of this breadth first layering that I've been doing? Well, if you think about it for a bit, the cycle it comes from this edge, and you know what's the highest? So the vertex of the cycle that's highest in the tree. Well, you take this vertex and you take this vertex and you take their lowest common ancestor. That's where the cycle closes. And so from this vertex up to the lowest common ancestor, I'm just getting closer and closer to the lowest common ancestor, closer and closer to the root all the time. And for this vertex, the same thing is true. I'm getting closer and closer to the lowest common ancestor, but also closer and closer to the root. So that means in this picture over here, I don't know if I take some edge, I'm not sure whether it's going to be in the middle or whether it's going to be here or even up here. That's not important. But there's this edge. It goes between, maybe it's a flat edge within one layer, or it goes between two vertices on consecutive layers. But you know, it goes up to the lowest common ancestor from here, and it goes up to the lowest common ancestor from here. So it only has, for each layer here, there's only two vertices of this cycle that take part in that layer, at most two. So in particular, if I only take, I don't want the whole cycle, I'll only take the part of it that hits here in between NA and NB, then I will only get 2 times the square root of n vertices in there. Okay. And in particular, if I can make it so that this cycle, not just, so forgetting about the NA and NB for now, if I could manage to pick this cycle so that there's less than or equal to 2n over 3 vertices inside and less than or equal to 2n over 3 vertices outside, then the cycle by itself would have been a separator, but maybe it's too long, too tall. On the other hand, if there's less than 2n over 3 vertices inside, that means there's less than 2n over 3 vertices in here. Certainly if all the vertices that are inside the cycle is less than 2n over 3, then certainly the ones that are inside the cycle and in between these two levels is also less than 2n over 3. And the same thing, if I add up everything here and here, all this pink stuff is also going to be less than 2n over 3 because it's all outside the cycle. And everything outside the cycle, including some stuff up here and down here, was less than 2n over 3. So if I could just find that cycle, which doesn't have more than 2n over 3 things inside it and doesn't have more than 2n over 3 things outside of it, then I'd be done. And that's a cycle that I have to make just by closing off one edge of this, breadth first search tree. Okay. Well, how am I going to find such a cycle? Two n over 3, that sounds familiar. Have we seen that somewhere 20 minutes ago? Yeah. In what context? Edge separators of binary trees. Are there any binary trees in this picture? Yeah, let's use the tree co-tree argument. So look at all the faces. And we have a spanning tree of the main graph, which is the BFS tree. And so now if we connect the faces which share an edge, that's not in the BFS tree, we'll get a spanning tree of the faces. And there. Okay. Good. So I know that that spanning tree has an edge separator that will have at most two-thirds of the faces on one side, and at most two-thirds of the faces on the other side. In this picture, well, in this embedding, that means if I take the BFS tree and close it there, what is the stuff on this side? It's the stuff inside the cycle. What's the stuff on this side? It's the stuff outside the cycle. Now, we're not quite there because, well, I was counting faces inside and not vertices. But I know that I won't get more than, so if I just do this, I will get some cycle which has less than or equal to 2f over 3 faces. Less than or equal to 2f over 3 faces. Which is not quite what we want, but you can probably believe me, since I've been fudging all the time anyway, that, well, if you look at what's inside here, we've got this big cycle. The cycle has some length. I'm not worried about that. What I'm worried about is the stuff that's inside it, the number of vertices inside it. And I know that that is less than or equal to 2f over 3. And by fooling around a little bit with Euler's formula, which is really specialized now, what's in here is something that's all triangles, and then a big face on the outside. You can convince yourself that it actually doesn't matter how long the cycle is, there's going to be less than 2n over 3 vertices inside that cycle. Okay. So the edge separator separates the faces in this nice way, and then you have to fight with Euler's formula for a little bit to convince yourself that that's good enough. That also controls the number of vertices that are inside or outside the cycle. Okay. All right. So that's the proof of the planar separator theorem. So what's the total size of the separator we get? Here we have root n vertices. If we take this layer, we have root n vertices because we're going to take all the vertices in this layer. And here we have root n, and here we have root n. So that's another 2 root n. So we get at most 4 times the square root of n vertices. Okay. Good. How is that useful? Well, it turns out to be immensely useful, but for the problem we're interested in, which is an efficient data structure for distance queries, here's what you do. You have your planar graph, G. You take your separator, S, you remove it from your graph, and that breaks your graph up into components. Not necessarily just two, could be lots. But no component has size bigger than 2n over 3. All right. So I'm going to use recursion on each of the components. So I will say I only have to worry now about queries for vertices where Vi is in one component and Vj is in a different component. So I only need to answer those kinds of things. Otherwise, if both things are in the same component, I'll answer it recursively. This separator has size square root n. So what I could do is have Vi remember its distance to every vertex in this separator. Okay. And so, you can compute a shortest path tree. In fact, you can do more clever than that, but you can get the distance from every vertex in this separator to every other vertex. So just think of it as Vi remembering all its distances to these vertices. And Vj also remembers all its distances to these vertices. And I know that if I want to get from Vi to Vj, I have to go through one of these vertices, because when I take this set away, Vi and Vj are in different components. So every path from Vi to Vj goes through those vertices, including all the shortest paths. So if I want the distance from Vi to Vj, all I have to do is ask, what's the distance if I go through this vertex? What's the distance if I go through this one? What's the distance if I go through this one? Take the minimum of all those. That will be the true distance from Vi to Vj. Okay. All right. And then you recurse separately on each component. So let's think about what that does. And what's happening here. So let's think about the space. So just for the top level of the data structure, I have this separator, and every one of the other vertices remembers its distance to every vertex in the separator. So this thing remembers root n things, this one remembers root n things. That's true for all of them. So that's going to be something like n times root n, which is n to the 3/2. And then I have to recurse on each of these components. And I'll just say that this is kind of a boring exercise. And 1, and 2. And in fact, I can even group them, so I can, even if I get 4 components, I can put them into 2 groups that are neither of which is really, really big. With the point being that when I do that, then this whole thing resolves to O of n to the 3/2. Okay. So you end up with a data structure that uses O of n to the 3/2 space. And the query time is O of n to the 1/2, or square root of n. Right? The query for 2 things is, if they're in the same component, I will query the recursive data structure that I made for that component. If they're in different components, then I'll look at this take the minimum over all of the element-wise sums here. Okay. So that, without the planar separator theorem, is, I don't know how you would do that without the planar separator theorem. Now, is that the best that you can do? The answer is no. You can do better than that, but not totally, not in all settings. So first the plus side. I mean, n to the 3/2 space seems like a lot. It's much more than n log n. It's much more than n. And square root n query time also seems like a lot. That's not log n or anything nice. But one nice thing about this is it doesn't care at all what the distances are. So in particular, I talked about the distance in the graph being the length of the shortest path. Length could mean the number of edges in the shortest path, but it could also mean if the edges have weights on them, then you take the path where the sum of the weights is minimal. And all of this works fine with that. It doesn't care about that. All of the recursion just cares about breaking the graph up into small pieces. It doesn't care anything about the weight. So it's nice in general. And a few more things. With a bit more fiddling, you can play around with this so that I can make the space bigger and the query time smaller, or I can make the space smaller and the query time bigger. But if you just do that, you'll always get that the space times the query time is n squared. That's what's happening here, right? N to the 3/2 times n to the 1/2 is n squared, and that's going to be true. And you can get that for anything here, which is space more than n, significantly more than n, and all the way up to n squared. So you can get the query time very fast. N squared would be just a lookup table in queries in constant time. That's great. But if you go down to the very first version of the problem that I mentioned when I didn't talk about weights or anything at all, just shortest path means number of edges in the path is minimum, then there's actually some very clever work that you can do to drop this by a lot. And that, if anyone is interested to read about it, it uses a very special property called the Monge property. But basically, it's used to solve this problem of finding the minimum here. And for that, you use a special separator. Let's say the simplest thing would be a cycle in your graph. And you have some vertex that's going to be outside the cycle, some vertex that's going to be inside the cycle. And you use the fact that, that not everything is possible. So instead of just adding all of these things up, you can actually treat this as a problem on a matrix and get this done in log n steps. It's very clever thing, but it only works for unweighted graphs. And then finally, I'll point out that just like what we did for adjacency testing, the basic thing where each vertex gets a list of length 5 plus its own ID, that gives you just a label for that vertex. If you give me the labels of any two vertices, I can test if they're adjacent. Well, the same thing is happening here, right? Each vertex gets a string of numbers, and an ID saying what component it's in. And it gets another string of those things recursively, but the length of those things keeps going down and down. So this vertex is only storing root n things, order root n things in total, which you can think of as its label. So it has a label of length root n. And that's true for everybody. And if you give me the labels of two things, then I can, by looking at their labels, I can tell exactly at which point they fell into separate components in this recursion, and then use that part of their label to tell you the distance between them. So that solves the distance labeling problem with labels of length n to the 3/2. It's been a long standing open problem to know if that's the best that you can do. What's known is that you cannot do distance labeling in less than, with labels of length less than n to the 1/3. So you need labels of length at least n to the 1/3. Labels of length n to the 1/2 are sufficient, but that gap is wide open and has been for more than 20 years now, I think. All right, so there's a good place to stop. Don't come to this classroom next week, join by Zoom.
Hi, Pat. Can I just say something?
Sure.
I'm going to be sending another email regarding my public contribution tomorrow.
Okay.
So I would appreciate if you could take a look at it, because I was having problem with the previous one.